First of all, welcome to everybody, and it's a pleasure for me to moderate today's episode of tinyML Talks, the series which is well known in the tinyML community. My name is Danilo Pau, and today I have the pleasure to introduce you Hadjer Benmeziane. Forgive me if I pronounce it not properly. She is a visiting researcher from IBM Research Europe, and today she will speak about her latest efforts in the field of advancing medical imaging analysis with multitask and hardware-efficient neural architecture search, which is a great topic, well in the scope of the technical topics of tinyML. But before to let her to start, let me thank the strategic partners, because this series, as well as many other events which take place within the scope of tinyML and organized by the tinyML Foundation, are possible thanks to the commitment and the support of the strategic partners. Let me name them one by one: AIZIP, Arduino, ARM, BrainChip, Edge Impulse, Embed UR, Efficient, Greenways Technology, Grovity, IMAX, ImageMob, Infineon, Inatera, Not AI, NXP, PNG, PIMIC, Pauling Technology, Qualcomm, Renesas, Schneider Electric, Sensimil, Sony, Silicon Labs, ST Microelectronics, Synaptics, Sentient, Tilke. There are two quite important assets in the tinyML community supported by the foundation, which are worth to keep in mind and to use. One is the Meetup. The Meetup aggregates a lot of members across many groups in many countries at worldwide level, and is important and fundamental for sharing knowledge and also for interconnecting each other, which is of paramount importance into the AI landscape, especially from a tiny point of view. The second asset is the LinkedIn. In the LinkedIn, there is the possibility to express your latest advancement and learn from the progresses of the others. We have many members and many followers, and this is a sign of great interest within the community. Furthermore, another important asset is the YouTube channel. In the YouTube channel, if you are interested to learn anything about tinyML, from hardware to software, from business to technology advancement, and latest evolution from many actors inside the tinyML community, definitely YouTube is the right place where to pick up the content that you need. Obviously, it's huge, the content, so you have the freedom to pick up what you need and to learn from it. So please take advantage of this huge repository that has been built thanks to the proactivity of many members and many efforts. Let me remind also the importance of the tinyML Research Symposium. First of all, this is a unique event that happens once in a year, and is co-located with the tinyML Summit happening in San Francisco. So we had the call for proposal, the paper has been submitted, and we are now going to review them. So stay tuned, because this is the capital letters scientific event, which is supported also by a strong and well reputed technical program committee. And also do not forget to plan your attendance to the symposium and to the summit in San Francisco. One of the many output of tinyML Foundation is the 2023 Edge AI Technology Report, which has been a success. A lot of content, especially useful for young practitioners into the tinyML landscape. a new report is also under preparation, and the plan is to make it available soon, likely after. So let me just quickly introduce Hadjer Benmeziane. She is the visiting researcher at the IBM Research Europe, specializing in hardware-aware neural architecture search for emerging AI accelerators, such as analog in-memory computing. She received her PhD from Université Polytechnique de Hauts-de-France in August 2023, following her Master and Engineering degree in Computer Science from École Supérieure d'Informatique in Algeria. Her work on analog neural architecture search received the prestigious IEEE Open Source Science Award and Best Paper Award at IEEE Service Computing 2022 Symposium. So congratulations, Hadjer. Her research focused on making hardware-aware neural architecture search more efficient, flexible, and practical, which is what we need in the tinyML community. So I leave the word to you, and enjoy the presentation.
Okay, thank you very much, Daniele, for the presentation. So hello, everyone. I'm here to present some of the work that I did during my PhD thesis at Université Polytechnique de Hauts-de-France, LAMI, with a collaboration with IBM Research. So this work is intended to advance medical imaging analysis and specifically segmentation using hardware-aware neural architecture search. So I'm really honored to present this work at the tinyML talks. So first I'll go over, so this is the presentation content. I'll go over the context and motivation why we want to automate the design of these medical segmentation models using neural architecture search. I'll define in the background the most common deep learning architecture that is used in medical imaging, which is the unit. And I'll also explain the most used components of hardware-aware neural architecture search. I'll introduce a benchmark that we created during my PhD, which is HW-NAS bench, that helped us compare different search strategies on medical imaging segmentation. And then I'll introduce one of our contribution, which is a multitask hardware-aware neural architecture search strategy on top of this benchmark. I'll have one section about other hardware platforms potential, and specifically the analog in-memory computing potential for medical image segmentation. And I'll conclude this presentation with some future perspectives. So as Daniele said, you can interrupt me anytime with your questions. I'm checking here the questions that you ask, and I can answer them as we go. So yeah, just a bit of context and motivation. Deep learning is used everywhere, as we know. It's used, and we want to make use of it in the medical field. So, for example, NVIDIA used the generative AI to really expand the data set so that we can have promising results on these medical imaging deep learning models. And also, there has been a lot of work done on medical tasks on wearable devices, taking, for example, PPG sensors and trying to estimate the pulse rate, or trying to detect a myocardial infarction based on the ECG, for example. But what we are most concerned about in this talk is the medical imaging segmentation. So our purpose is to segment a tumor, for example, in the brain MRI. So we have a brain MRI as input, and we want to segment to find it and to segment the volume of the tumor precisely. And one thing that I was surprised about is the number of FDA-approved deep learning algorithms that are currently done. So there have been more than 35 FDA-approved medical AI algorithms out there, from detecting or segmenting the arteries in the heart, or detecting the nuclei in the eyes, and also the stroke detection on CT images. So there have been a lot of work done, and a lot of approved work that are working in real life scenarios. And what we want a growing number of these deep learning algorithms that are helping radiologists in different medical specialties. So we want to automate the design of these algorithms to enable multitask benefits. So this slide summarizes the context and motivation. So we know that deep learning models are really accurate, they are good, they automate and help radiologists' tasks, but we need an urgent need for efficient AI solutions that can help us automate the design of these architectures for multiple applications. We know that current unit-like architectures are really slow, they are very large, they really require expensive laptops, and currently most radiologists, like most of the common radiologists, don't have that at hand. And also, compared to other tasks that are targeted by neural architecture search, so we usually use neural architecture search for image classification, for object detection, but these hardware aren't critical, or these tasks, sorry, aren't critical in terms of robustness, certainty, and interpretability, and these objectives are really critical in medical tasks. So we really need to take these critical objectives and include them or incorporate them into our search algorithms. So the most common deep learning architecture is this unit architecture. And although it has been like published on 2014, still most of the segmentation models use it either as a backbone or use it directly. So it has this U shape, and thus the name UNet. It has a U shape. So you see that there is a sequence of different, maybe you can use, sorry. Yeah, so there is a sequence of different convolutions here, and in between you have the common max pooling to reduce the feature map size. And on the upside of the U shape, you have an up convolution, which is a transpose convolution. The goal of it is to increase the feature size again, the feature map size again. Now, the role of this U shape allows us to detect really small objects, but also big objects at the same time because of this U shape, basically. And this is why it's used a lot in medical settings, because in medical settings, tumor can be as tiny as an ant and as big as something as something visible in the image, but it can also be something that is not really visible in the image as well. And on the other side, hardware-aware neural architecture search has been here for a few years already, and it has the three main components. So you have the architecture search space that defines all the possible architectures that we can define, and then you have the search algorithm that looks into this search space, trying to find the best architecture. And of course, this best architecture needs some kind of metric to say, okay, this is the best. And this metric, so this is why we need two other like components that evaluate the accuracy and also the hardware efficiency. So the accuracy can be evaluated with different strategies. Of course, we cannot train all the sampled architectures. So just to give you an idea, the architecture search space can contain billions of architectures. So we cannot train all of them to say, okay, this is the best architecture or something like this. So we cannot train them all, and we require some kind of estimation strategy here. For the hardware measurement as well, we cannot deploy all the architectures and find out what is the latency or what is the energy consumption of these architectures. And we need some kind of performance predictor or some kind of estimator that can tell us, okay, this architecture is more hardware efficient than this other one. Now, in this plot, in this figure, you can also see some optional things or some optional components in neural architecture search. So first of all, the architecture search space can be optimized. So we can remove some operations if we see that these operations are neither good in terms of accuracy nor good in terms of efficiency. So they are really slow or they are not given any increase in the accuracy of the models. And we can also have a hardware search space. And in this case, we're looking at architectures that are good in terms of accuracy when looking at the architecture search space, but also their hardware configuration that is associated with them. So the number of PEs, persistent elements, or the tiling parameters to really optimize the latency or the energy efficiency as we go. And one other thing that is common is to have, once we find the best model, we can also like compress it further or add some additional optimization on top of it, such as quantization or pruning. So given these two fields, we know that hardware-aware NAS, so hardware-aware NAS is actually the topic of my PhD. So I've been working a lot on hardware-aware NAS for image classification, for object detection, and for keyword spotting as well. But then I said, okay, what's the most task that I want to advance, or a task that I want to contribute to, and that was the medical task. So how can we apply hardware-aware NAS to medical imaging analysis? And actually, there are various neural architecture search that are implemented for medical segmentation. And when I looked into them, I saw that these are actually so these are actually using different search space and different definition of their architecture search space. So they use different things. So how can we really say that this one is better than this one if their basic search space is actually different? So in this case, we started by thinking, how can we design a neural architecture search benchmark? So I'm just going to stop here to answer one question that was there. And so Imola is saying, is the performance predictor available open source? So for example, the performance predictor for the hardware measurements, I know that Edge Impulse, for example, use a compiler with a certain lookup table. So you can look at this. Or you can also see proxyless NAS that also provide the lookup table for these performances. And they basically have the performance for each operator, and then you can sum them up to know what's the performance of your end-to-end model. And in our benchmark, we also put these metrics out there using the lookup table. So I'm gonna present it as well. Yeah, so as I said, because we can compare them, because we can compare these medical NAS, and we can't come up with a novel strategy and just come up with a novel search space where it's the best. So we need some sort of standardized benchmark for these kind of tasks, specifically these tasks, or specifically the unit architecture, so that we can compare the different architectures together, or the different search together. There is also one thing where we can see that for two architecture search methodologies, even if they use the same search space, we saw that they use different data pre-processing for the same data sets. So they achieve better results, and we don't know if it's because of the data pre-processing or it's because the search is more efficient. So the data pre-processing also needs to be the same for all the methods when we test them, so that we can say, okay, our methodology is better or not. And thankfully, for medical tasks, we have a lot of different data sets out there, and among them there is the medical segmentation decathlon. So the medical segmentation decathlon offers 10 different tasks with 10 different data sets. And you can see that you have for the brain, for example, an MP MRI modality. For the lung, it's a CT modality. You have a really variety of different modalities, variety of different inputs, and variety of different tasks. So on top of it, we actually designed our medical NAS benchmark. So for each of these tasks, you have a number of architectures that were trained and the different objectives that are available in the benchmark. So we actually trained our benchmark on 11 different tasks. So the 10 tasks that are coming from the medical segmentation, to which we added the X-ray dataset for pneumonia detection. And the goal is to add a different modality. So the X-ray modality wasn't available in the medical segmentation decathlon, although we also use kind of unit-like architectures for the X-ray pneumonia detection with a split. I will explain it in a few slides, but basically we can use the same search space for all of these tasks, and we want to enlarge our tasks or diversify our tasks for all medical imaging tasks. Now, the benchmark is represented as a super network, and this is why you can see this huge number of architectures, 1 billion architecture, 262K architectures, and this is based on the super network architecture. And we're using the weight sharing methodology to estimate the performance score. So that means that we're training the super network as a whole once, and then we validate each subnetwork using the weights that are shared between the different subnetwork of the super network. And of course, we're using a unit-like representation for the super network, as we've seen that this is the most used architecture for super network. Just a comment on that. Currently, there are some swing unit-like architectures, and we are planning to extend our search space with attention-like blocks. So the way we create our super network, first we have a super network per task. And for each of these super networks, we actually design it in a recursive way, which means that for each of these blocks, we can have multiple layers, multiple possible layers per block. And each block in the downsample part of the unit has its opposite block in the upsample part of the unit. And the goal of this is to shrink a little bit the size of the search space so that it can be explorable in a practical manner, and we don't have a lot of different invalid or non-valid architectures or subnetworks. So at the end, you have the segmentation head. Of course, if you want to do a segmentation task, you go from the downsampling to the upsampling, and then you have the segmentation head for the number of pixels and if they are glioma or any other task. And of course, if you want to do a detection head, then at this point it stops.
You haven't really finishing getting to them because some of them went out.
Yeah, at this point, if you want to do a detection head, for example, if you want to detect a pneumonia, then you split your unit and you stop just here, and that's shrink the search space based on the task. And so this slide presents the list of different blocks that we have in our super network. You can see that we extend our search space with 2D convolutions as well as 3D convolutions. We have different blocks that merges between different 2D convolutions with different batch norm or a bit different activations. And for each of these operations, we have the respective upsample operation that goes with it. So as I said, we use the weight sharing strategy to verify or to rank the architectures or to extract the score or the performance of the architecture. Now, to verify that the weight sharing strategy is really good or efficient in our search space, what we did is we took 10K architectures per task. We extensively trained each of these architectures independently of the super network. And then we compared the rank of these architectures based on a rank that is provided with the weight sharing methodology and a rank that is provided with a surrogate model. And the surrogate model was trained with 80% of these 10K. So it was extensively trained. And you can see that for all of these tasks, we can actually see that the weight sharing methodology surpasses the surrogate model in terms of Kendall-Tau correlation. So the Kendall-Tau correlation is a ranking correlation. And you can see that it actually outperforms the surrogate model, except for the lung. In the lung tumor segmentation, we can see that it's really close. So this is why we went for the weight sharing for all of these architectures anyways, like even for the lung tumor. On the left of the slide, you can also see the distribution of the performance, and you can see that you have actually a decent range of different performances for each of the tasks. And this is quite a challenging benchmark to reach the best architectures in each of them, because the architectures themselves look a bit similar, but the performance range is really wide. So I see that one question, Ayman is saying, do you apply quantization and pruning within operations used in the search space? So this is a pure neural architecture search benchmark. We don't apply any quantization or any pruning. So on top of this on top of this benchmark, with all the architectures for each of the tasks, we actually evaluated also the hardware efficiency. And the hardware efficiency was evaluated on two different hardware platforms. So you have the Raspberry Pi 3 and the laptop. You can see that the Raspberry Pi, I want to highlight that here, the Raspberry Pi has only 1 gig of RAM. So it's really a small embedded device, basically. And these are the results that we get from, or the distribution of the latency and energy consumption on the two devices. So we actually deployed 10K of the architectures, and for these 10K, we actually computed their latency and also their energy consumption. So this is provided in the benchmark. But for the rest of the architectures, because we have 1 billion architecture for some tasks, so these are actually estimated using a lookup table. And one interesting thing that we can see on the Raspberry Pi, not really, it's also it's a common insight that we see on the laptop, but not really that like shown in the figure. But you can see that tasks that have the same modality or same volumes as inputs have approximately the same latency. One other thing you can see is that the energy consumption, for example, has a decent, like a really good range, or a wide range, or not good, but it's a wide range of a different energy consumption. So it's good to search on top of this benchmark for energy efficient architectures. So one other experiment that we did, it's the cross datasets ranking evaluation. So one question that we had, because of the similarity in medical imaging datasets, although they are different, I agree, the lung is completely different than the brain, but the images are similar in some ways. So we asked ourselves, is there a single architecture that can be used for all medical imaging tasks? So is there the one architecture that is multitask, and I can use it for all of these tasks simultaneously? So we took these 10K architectures from each of the, we took 10K architecture from each of the tasks. We ranked them and we compare the ranking. So the question is, are these architectures, because they are the same architectures basically, are these architectures ranked the same on these different tasks? So you can see, for example, if you take the lung tumor segmentation and you take the pancreas segmentation, 90% of these architectures are similar, of the top architectures are similar. So you can see that, okay, if I take an architecture, I train it for lung tumor segmentation, I can take the same one and train it again for pancreas, and it's also the best. It's still a good result on both data sets. And this is one of the things that we really wanted to highlight, in the sense that we can do a multitask search on all of these tasks and came up with one architecture, just one, to deploy it once and that's it. And that architecture will be good on all these tasks. And a similar conclusion you can that we see actually that we see on the hardware efficiency, we also see it on this diverse like multitask analysis. We see that our data sets that have the same modality usually have the same ranking of these architectures, and they than other data sets basically. So one last experiment that we did on these benchmark is we gave some baselines on top of this benchmark. So these baselines include evolutionary algorithms. So an evolutionary algorithm that a simple evolutionary algorithm that we run on our super networks, a random search that we also run on the super networks. And then there are 3 different state-of-the-art search methodologies that are not from us, but these search strategies use different algorithms. And basically we run them on our benchmark to see what results can we get. So just to give you a quick explanation on the methodology, so you have a mixed search, C2FNAS. Both of them use a 2-phase search where they look for the topology, they look for the general connections, and they also look for the operation itself. So the cell inside the layer, what kind of cell will it run? So basically, we run them on top of our neural architecture search. The difference between them is that mixed search is purely differentiable, so we can apply it directly on our super network. C2FNAS is an evolutionary search, so we actually use the performance scores used by the weight sharing methodology as an objective, but we use their algorithm or their evolutionary search. The last one is BixNAS. So BixNAS is also a 2-phase, but they actually use, so it's not a 2-phase in terms of connections and operations, but they actually use a differentiable neural architecture search to narrow the search space. And then they use a progressive evolutionary search. So we also use that on top of our benchmark. One comment that you can see is that there is no method that is the best everywhere. So you can see that mixed search, for example, is good at brain tumor segmentation, lung tumor segmentation, liver, and you can see that C2F-NAS is good at hippocampus and colon. You can see that BIX-NAS is good at pancreas. So there is no method that is the best everywhere. Okay, so let's conclude the benchmark part of our talk. Let me just see if there is any questions. So Jeremy is asking, are training hyperparameters, learning rate, early stopping, batch size, optimizer, etc., part of the NAS decision variable set? Yeah, that's a really good question. We don't do we don't include them as part of super network search, but once we find the best architecture, we do use Optrina to do hyperparameter optimization on each of these networks to optimize the training. But this is only once we find the best architecture. Arun is saying, I have a few questions. Do we have to run HW-NAS on GPUs computers? And I am curious about knowing the running time on the experiments if it is observed. Yeah, so of course you expect that creating a search space required a cluster of different GPUs. So we actually used a cluster of different GPUs to create this benchmark. Now the search itself doesn't require a GPU, but it takes quite some time. So it's different from mixed search C2F-NAS and BIX-NAS. It's different from one super network to the other because the search space differs, or the number of the search space size differs. But generally, it takes so for mixed, generally it takes 2 to 3 days as an average of all the methodologies. And then Mohammed is saying on which kind of biomedical images this benchmark architecture are based, 2D, 3D, and 4-dimensional. Okay, that's really a good question. I wanted to emphasize it here. I don't know if it was clear. So each of these tasks or each of these super networks has actually a different input or has a different volume. So the NP-MRI of the brain tumor segmentation is a 4-dimensional. The hippocampus and the heart are 3-dimensional. The lung are 3-dimensional CTs, but the X-ray is 2D. So each one is different. So we actually have a variety of different volumes and data. Okay. So let's now that we have a benchmark, let's discuss how do we create a multi-objective search? Like what kind of search can we do on top of this benchmark? So what we actually thought about is inspired from a pruning strategy. So because we have a super network that is already trained thanks to the benchmark, and if we have to do another search on another data set, of course we have to train another benchmark, another super network, and this is why here the first step is to train the super network. But our idea is actually inspired from pruning. And in the pruning strategy, and you can look it up in this paper, basically what they do is they give an operation importance score based on the weight of that operation. And if that operation is important, they keep it. If it's not, they prune it. And this is done in a fully connected neural network. But if you take it to a step or step high, like in a high level way, you can do the same thing for a super network. So what we do is we explore a super network from bottom to top, and for each of the layers, or for each of the layers, we check the block importance score. So is that block, is this operation at this point important or not? Based on the weight of that layer multiplied by the accuracy, the validation accuracy that we obtain at the end using all the sub networks that uses that block. So if that block is important, then we keep it. It's the most important, basically. Then we take it, and this is our path. So it's pretty straightforward. We just explore the super network from bottom to top, and we just select the most important block each time. And just one comment here, if we want to go for a multi-objective search, what we actually did is we explored the Pareto front. We extract the Pareto front by relaxing the number of selected blocks. So rather than saying, okay, I'm going to take the most important block, I'm going to take the 3 most important block in each layer, for example. And then one thing we did is, of course, we want to have something, some search objective that is like multi-objective in a sense. And also we want to have this multitask. I didn't mention anything about multitasking for now. But basically here what we want for each of the blocks, we want to maximize the validation accuracy. I'm using here accuracy just not to confuse everyone with a performance, like a hardware performance. I'm using accuracy, but it actually depends on the task, and it's more like a task-specific performance. So it can be the DICE score, it can be the Jacquard score, etc. So here, for example, we want to maximize the accuracy over the hardware awareness. For us, the hardware awareness is measured by latency. It can also be energy consumption. Plus, we want this some sort of estimation of the task generalization ability. Now, given that we have a block importance, the task generalization ability is done by checking the block importance on other tasks. So if you have, for example, 2 different super networks, you can see here and here, you explore them both from the bottom to the top. And for each layer, you don't only see if that layer is the most important in that super network, but you also see if that layer is important in other super networks, so that you can define some sort of task generalization ability. And this is the way we do it. Of course, for each of them, we define like, so the alpha here is the validation accuracy. The sigma here is the cosine between the different weights or the different block importance scores in different super networks. So when we validate MTMS, we validate it on top of 3 different scenarios. So the first scenario is called the MIAS scenario, the medical imaging architecture search. So this is the classical hardware-aware NAS, where we just maximize the accuracy over the latency, for example. The second scenario is the MTMS, or the multitask MIAS. Here we're adding the task generalization ability, as I explained. And the last scenario is the most interesting for me, where we relax the number of blocks that we extract per layer. So what we are saying here, we're saying if the super network as a whole can be deployed on our end device, then you can give me a super network where each subnetwork can do a different task. So they can share maybe a layer together, but they can also split to do brain tumor segmentation in one side and lung tumor segmentation on the other. So this is MTMS. So you relax the number of blocks that are extracted per layer, so that we can have different subnetworks that can extract, that can do different tasks, basically. So these are the initial results that we obtain on brain, hippocampus, lung, liver, prostate, heart, and pancreas. And compared to the state-of-the-art search methodologies that we have, we can see that we actually outperform them in general. And then you can see that the MIAS, the classical hardware-aware NAS, is the best. Generally, it's always the best. And this is because we're looking for an architecture that is the best in terms of accuracy or in terms of DICE score here. The second one, the MTMS, when we constrain it to find one architecture that is good in all of the tasks, of course, we lose some DICE score or some performance, where, we're doomed to lose it because we want something that is really good in all of these tasks. And if we look into the MTMS, where we relax the super network to allow for subnetworks that are good for different tasks, here we can see that we actually, even for some tasks, outperform the MIAS. And this is because we outperform it because we have some shared weights that are actually extracting more features than the actual first model that we extracted for only the brain task. So following the medical segmentation decathlon, so if you look at the medical segmentation decathlon as a competition, they actually give 7 tasks that are here, these 7 tasks initially, and they kept 3 mystery tasks. And then what we do is we take these 3 mystery tasks and we ask ourselves, can we, based on the multitask results that we obtained here, apply it to these mystery tasks? So can we find an architecture that is good for these tasks, but then apply it for the mystery tasks? And this is interesting because even without even like this, we can find an architecture that outperforms current state-of-the-art architectures on these tasks. And you can see that MTMES C, for example, T here, the T refers that T here refers to the fact that we added some fine-tuning to the architectures that we find. So that means that we find an architecture that is multitask for every other task, or for all the 7 tasks here. And then we take the column data set and we actually fine-tune that architecture for this task for a bit. And this is commonly done in all if you want to transfer your architecture to another data set, of course, you're going to fine tune it for some epochs. And this is what we did here. And you can see that the results are actually better for our search results or for our architectures. One data set where we don't outperform state-of-the-art results, and you can see that C2F-NAS is actually slightly better with 0.03%. And this is the chest data set where you have X-ray images. Now note that all of these tasks only use either CT or MRIs, and they weren't trained for X-ray. So it's understandable that an architecture or search that is specific for that data set would find better results. Okay, so before I go for other hardware platforms, I'm just checking if there is anything, any question. Okay, Mohammed is saying, neural architecture search similar to grid search, requiring the training of multiple models to determine the best one. Also, does it primarily focus on small model, or you consider the optimization as the next step after NAS? So we don't consider any optimization as a next step after NAS. So we just do we search for architectures that are good in terms of energy, latency, deployable on the hardware, and accurate. And we emphasize on the accuracy basically, or we emphasize on the task specific performance. The first question, I don't quite understand it. So neural architecture search is not only grid search. So grid search, I agree, it's part of you can consider it as part of neural architecture search, but it's not. Neural architecture search is much more than that, and I hope it's much more than that. So we actually use evolutionary algorithm, we use super network, we use different strategies to minimize the number of times we need to actually compute the performance of that architecture. So you can look at it as grid search looks at the whole search space and evaluate each one of them. But we actually, in a smart way, explore that search space to find the best one. Peter is saying, how can you be confident that the best result for each architecture isn't the result of successful random initialization without repeated runs for every architecture to test this? The best architecture could be a result of lower. That's a really great question. And we actually, I didn't put here the standard deviation of different runs, but these are actually the mean of 5 different runs in all of our results. But I agree that we need to somehow make sure that the results are consistent. And in neural architecture search, that's quite hard to do it more than 5 times, because each time you have to train these architectures and you have to really evaluate them. So it takes a lot of time. But we actually did it for 5 times. Thanks you for the question. Okay, in the context of multitask learning, is there a global loss function that is composed from multiple partial losses for each task? In this case, do you need any normalization process for each of the? Mohammed, that's a really good question, but I didn't look for, there might be a multiple partial loss like that compose a global loss. But I don't know about this, but as you understand, we're just looking at an architecture, like the different operations that works well on the different tasks, and not just like different architecture that are trained with a single loss. But there might be. So I'll start now another chapter of the presentation, and this will highlight some analog in memory computing potential. So just to give you a bit of background, analog in-memory computing computes vector matrix multiplication directly in the memory. So in-memory computing generally computes the vector matrix multiplication directly in the memory. So they avoid having the von Neumann bottleneck where you have to go back and forth between processor and memory. So there is less data movement, hence more data, more energy efficiency. However, in analog, you have to deal with a lot of different noises that are inherent to the actual hardware. So when you find, for example, when you have a model that is accurate, that accuracy is 94%, for example, with time, when you deploy that model, with time, you can see a small drift in this accuracy. So over time, you can see that the accuracy actually decreases because of the weight that you actually write on these devices actually changes and the accuracy decreases. So in this kind of hardware, you're not only gonna find like an architecture that is accurate, but you also think about robustness or noise resilience. So we actually started with a work that we did on image classification, visual wake word, and keyword spotting. So that work is published on IEEE Edge, and this work is actually based on a ResNet-like search space. But the most important component here is how we develop the surrogate model, or how do we develop an objective function that can tell us if that architecture is good or not. So here you can see a comparison between ResNet 32 and analog NAS, for example. And you can see that ResNet 32 has a really high drop after 30 days. It has also like a 1-day standard deviation that is really increasing. And so this is why we choose these objectives. Oh, sorry for the numbers here. Okay, so the first objective is the 1-day accuracy. That means the accuracy up to 1 day of drift. We also want to maximize or minimize, the accuracy variation over 1 month. So we want to minimize this slope here. And we also want to minimize the standard deviation. So we want our results to be consistent each time. So this work has, I did it actually during my PhD and during an internship at IBM Research. But after that and after my internship, we started this work called Analog in-Memory Computing with Uncertainty Quantification for Efficient Edge-Based Medical Imaging Segmentation. And this project, I'm going to share with you some initial results where we explored different models in brain tumor segmentation and spleen segmentation and nuclei segmentation. And you can see that here we actually evaluated different hardware. So you have or architectures. You have the UNet, you have the UNet++, and you have the Swin UNet that I talked about. And some of the key insight that we have here is that transformer-based models are more resilient to noise than these pyramidal architecture where you have a convolution and then the feature map decreases over time over the architecture. And also due to the hardware we're training, because you have to train it with noise. So just like quantization, when you train with quantization, you need to do quantization aware training so that the weights are better and the accuracy at inference is better. So you have to do the same thing. Doing hardware training means that you inject some noise during the training so that your model is more reliable and it's more like it's more robust to that noise. What we have seen a nice side effect of this hardware training is that the analog inference becomes more reliable and more certain. So the models are actually more certain because they are trained in hardware training, even though the inference has some noise in it. And these results were explored on these 3 data sets based on the fact that they are different enough. And this is why we chose nuclei, spleen, and brain. Okay, so just as a conclusion, I'm sorry I took a lot of time, I believe. But yeah, just as a conclusion, we're really proud to present this MedNAS bench, this benchmark benchmark for medical imaging analysis. The benchmark is available, although the API, we're still working on it, and I'm going to talk about it in a minute. So yeah, I also discussed MTMS, which is a methodology for multitask search, and I discussed some of the potential of analog in-memory computing for the medical imaging analysis to enhance certainty, but also to explore more efficient hardware. Now, in the perspectives, we're actually increasing the collected objectives in our benchmark. We're actually looking to target more hardware platforms. We're collecting more objectives in terms of certainty, in terms of robustness, etc., and interpretability and fairness. And we're also improving the API access. So for now, when you look at the subnetwork, it takes a bit of time to look it up and extract it from the super network. So we're actually trying to improve that speed up this access so that everyone can use it in a nice way. And we're developing a search process that not only look at the multitasking, but also look at the analog in-memory computing noise resilience objective. So yeah, thank you very much. I hope everything was clear.
Thank you so much, Hadjer. I think there is still one question pending. You mentioned that you trained from scratch for performance estimation. Can't you avoid this by adopting other techniques such as hyper networks or weights normalization?
Okay, so the performance estimation wasn't trained. You can say that it's trained from scratch, but it wasn't trained. It's not a network that we trained. The performance estimation, if you mean like the hardware latency and energy consumption estimation, what we do is we build the lookup table. So for each operation, we say, okay, that operation on average, it takes this latency, and that operation with different hyperparameters, of course, takes also this latency, etc. So we build this giant table. And then if you give me an architecture, I'm just going to sum all the operation latency one per one, and then I give an estimated latency for that architecture.
Thank you so much. In general, there have been a lot of appreciations and compliments within the chat for your really great presentation, Hadjer. I have a question before we conclude your talk. Any comment, any experience about trying to constrain the complexity of the search? I mean, imagine that you receive a budget. A budget can be you need to complete within a certain time, considering the computational assets you have available, or the machine you have available, or things like that. Did you experience also playing with a constrained amount of time to exploring the potential solution to be deployed?
Yeah, that's a really interesting question. So in medical or in this work specifically, we didn't do that because we wanted to really see where it goes and keep it like let it for a while and see what it goes. But we did that for image classification and some other tasks where we wanted to have, okay, we capped the number of hours, for example, for the search algorithm, and we say, okay, you have only 5 hours, try to find the best architecture that you have, or you have only 24 hours and try to find the best architecture. The bottleneck of neural architecture search is still this evaluation. So if you use like a really accurate evaluation, sometimes it beats other, even if you give it only 5 hours as a search time. But it depends on a lot of things. So if a search space, for example, has a wide range of different architectures, usually if you have an evolutionary algorithm, we see that after a few hours, it finds a good region where you have all the good architectures. So you may find like a 94% architecture, and the best one is 94.2 or something. So you may be okay with that. But sometimes if the search space is really like wide and you let the evolutionary algorithm, after a while you see that it's still stuck in the 60% architectures and it cannot find the region where you have 90% architectures. But that's a really interesting experiments to do, actually.
Thank you, Hadjer. There is also a question I missed. I'm sorry. It's about digital in-memory technology, if you had experience with that.
Yeah, that's a really good question, but I don't have any experience with digital in-memory computing.
And maybe another question from my side, personalization. You know, for example, the neural networks that will be the results of the NAS will perform on average cases, plus minus something, but not for all. And maybe there are rare cases where they cannot detect or provide a suggestion to the doctor how to handle personalization or situation which are really out of the statistics.
So there are actually some neural architecture search strategies that include some human feedback or personalization. So you look for an architecture that is good for a certain time, and then once you find that, you can have a personalization metric or a human feedback that comes and tests the architecture and gets changes the trajectory of the search so that it's better. So there are some works like this, but I honestly didn't look into it here.
Okay, Hadjer, thank you so much. Your presentation was really great, and I enjoyed it. And I hope the same is the same shared from all the community. I'm sure that the questions you received are a strong sign of interest. And thanks so much to keep also the discussion interactive and addressing the questions while you were presenting the slides. This was really appreciated. Before to conclude, let me ask you the control, and let me go toward the end of the presentation. So we learned a lot from Hadjer within the today episode of the tinyML Talks series. And the series, as well as many other events, are possible thanks to the strong support of our strategic partners, which I mentioned at the beginning, which provide continuously commitment and support to make it happen events like that, as well as many others. Let me also remind what are the executive strategic partners, one by one. Qualcomm, Cynthia, the Platinum Strategic Partners, Embed UR, Sony, the Gold Strategic Partners, ARM, Edge Impulse, Infineon, Innatera, Renesas, ST Microelectronics, Synaptics, the Silver Strategic Partners, AEZIP, Arduino, BrainChip, Efficient, Greenwaves, Groverty, IMAX, ImageBob, Nota AI, NXP, PNG, PIMIC, Polytechnology, Schneider Electric, Sensible, Silicon Labs, and TDK. So thanks so much again, Hadjer, for your time, for your dedication, and to be very active today and energized in all the part of your presentation. That was much appreciated. And soon the video and the slides will be available. And thanks again to the tinyML, Rosina, Evgeny, and all the foundation to support tinyML Talks. Thanks, and have a nice day. Bye.